Today we're going to talk about polyprotic acids, acids that give more than one proton per molecule, and how we can deal with them in pH terms. We're also going to talk about the acid-base properties that salts may have, but before we do any of that, we're going to tackle a few QuizKin questions. This first question is asking, what's the pH of a 0.2 molar solution of acetic acid, HC2H3O2, and Ka is given as 1.8 times 10 to the minus 5. Let's go to a bigger workspace and solve this problem. The acid is HC2H3O2. This is a weak acid, so we'll see reversible dissociation, and we'll get protons like we always do for an acid, and in this case the acetate ion. Ka for the acid is known to be 1.8 times 10 to the minus 5, and we want to know what's the pH if we start out with a 0.2 molar solution of acetic acid. So in our I line of our rice chart, we would put 0.200 for acetic acid, and then assuming that nothing is dissociated initially, those would be zeros. The change, stoichiometry is 1 to 1, so it's minus x plus x and plus x, so that at equilibrium, 0.200 minus x is the concentration of acetic acid, and x will be the concentration for both acetate and H+. Ka, remember, is the concentration of products raised to their coefficients divided by the concentration of the reactant, which in this case is just the initial acetic acid that we started with. In terms of our chart, at equilibrium, x squared would be the numerator, and 0.200 minus x would be the denominator, and that's equal to 1.8 times 10 to the minus 5. Now I'm going to make the assumption, because 10 to the minus 5 is fairly small, that I can ignore the x in the denominator. So we'll say that this is approximately equal to x squared over 0.200. So now to find x, I will just take 0.200, multiply by 1.8 times 10 to the negative fifth, and then take the square root. X turns out to be 0.0019, and that would be the H+ concentration at equilibrium. Now before we move on, let's just take that 0.0019 and compare it with the 0.2, because we made the assumption that it was so small we could ignore it in the denominator of this Ka expression, and in fact it is really small. If you subtracted 0.0019 from 0.2, it wouldn't change things when significant figures are considered. So that was a valid assumption, and of course the 5% rule would say, is 0.0019 less than 5% of 0.2, and it is far less than 5%. So now that we know the H+ concentration, we can calculate the pH. So pH, remember, is equal to the negative of the base 10 logarithm of the H+ concentration. So in this case, pH is minus the base 10 log of 0.0019, and that works out to 2.72. And that number makes sense because this is an acid, and that pH value is less than 7. This question is asking, what's the pH of a 0.1 molar solution of acetate ion? This is actually a related question, and here's why. Remember when we saw the acetic acid dissociate and create H+ ion and acetate, what we were really seeing here is an acid and its conjugate base. There's a relationship between the Kb for this conjugate base and the Ka for this acid. So that should allow us to solve this problem. So if acetate ion, C2H3O2 is present in an aqueous solution, like all bases, it's going to react with water, and it will reach dynamic equilibrium with hydroxide ion and the conjugate acid of the base, which is acetic acid. Kb for this reaction is going to be equal to Kw divided by the Ka for the conjugate acid, which we just had in the last problem. So Kb here is 1 times 10 to the negative 14 divided by 1.8 times 10 to the minus 5. And that turns out to be 5.6 times 10 to the minus 10. Now let's make a rice chart. We've already got the reaction here. Initial concentration, well, this is a 0.10 molar solution. Water, remember, we don't care about because it's not in our equilibrium expression. hydroxide and acetic acid concentrations are zeros initially. The change, there's one-to-one stoichiometry, so we lose X for both reactants and we gain X for both products. At equilibrium then, our concentration of acetate ion will drop to 0.10 minus X. Water we are still not concerned about. And hydroxide ion concentration and acetic acid concentration will both be X. So Kb is 5.6 times 10 to the minus 10th, and in terms of our chart it is OH minus concentration, which is X, times acetic acid concentration, which is also X, divided by the concentration of acetate, which is now 0.10 minus X at equilibrium. Again, we'll make the assumption that this is approximately equal to X squared over 0.10, just to make the arithmetic easier. So that means that X will be equal to the square root of 0.10 times 5.6 times 10 to the minus 10. Since that negative 10 is in the exponent, I think that assumption of dropping the X is even more valid in this problem than it was in the last. Well, X, which is equal to the concentration of OH minus, turns out to be 7.8 times 10 to the minus 6, which is obviously far less than 5% of 0.1. So our assumption was valid. Well, now that we know that, we can find the H plus concentration. The H plus concentration is going to be just Kw divided by the OH minus concentration. So 1 times 10 to the negative 14th divided by 7.8 times 10 to the minus 6th. And that turns out to be 1.4 times 10 to the minus 9th. Our objective was to find pH, so that's why we did that. So we can take the negative base 10 logarithm of that H plus concentration, and that will give us our pH value, and it's 8.87, appropriate number for a weak base. Now let's take a look at polyprotic acids just briefly. There are two kinds of polyprotic acids that we're going to look at here. One is diprotic acids, and the prefix di, you might know, means two. So these are acids that yield 2 protons per molecule. Ionization is going to occur in 2 steps for these diprotic acids. So an example of that would be H2SO4, strong diprotic acid. The first step of dissociation is going to be it'll yield 1 proton and then the bisulfate ion, HSO4 1-. Ka for this step is huge. It's much, much bigger than 1. HSO4 1-, the product of this first dissociation, is itself an acidic anion. So it's going to dissociate and give you more H+, and then the sulfate ion, SO4 2-. Ka for this step is 1.2 times 10 to the minus 2, which is still a fairly large number as far as Kas go. However, most of the H+ is going to be released by the first ionization. Tryprotic acids, you can probably guess what they mean. Tri means 3 protons. So these yield 3 protons per molecule, and they're going to ionize in 3 steps. So here's an example of a triprotic acid, phosphoric acid, H3PO4. The first ionization is H+ and H2PO4 with a 1- charge. Ka for this first step is 7.5 times 10 to the negative 3rd. Then the H2PO4 that was generated in that first ionization is itself an acid. So it's going to reversibly dissociate to give you H pluses, and HPO4, which is a 2- ion. Ka for the second step is 6.2 times 10 to the minus 8th. And then the HPO4, which is the product of the second ionization, HPO4 2-, will dissociate further to give you H+ and the phosphate ion, PO4 3-. And Ka for that third step is much smaller than even the second one, which is 4.8 times 10 to the minus 13. In weak polyprotic acids, as I mentioned before, almost all the ionization that produces H+ is going to occur in the first step. So let's look at an example to just sort of verify that. We're supposed to find the concentrations of all species in a 4.5 molar solution of H3PO4. Let's try it out. Let's start out by looking at the first ionization here, H3PO4, dissociating reversibly to give you H+ plus H2PO4 with a 1- charge. And remember, Ka for this first step is 7.5 times 10 to the minus 3rd. Here's our Rice chart. The initial concentration line, 4.5 was our molarity. So no dissociation has taken place, so we have zeros there. The change is 1 to 1. And so at equilibrium, we have 4.5 minus x, and then x, and then x. So Ka, which is 7.5 times 10 to the negative third, is equal to x squared divided by 4.5 minus x. Now 10 to the minus third is fairly small, but 4.5 is really big, so I think it's pretty valid to assume that that x here is ignorable in the denominator. So we'll do that, and we'll say that this is approximately equal to x squared divided by 4.5. So that would mean that x is equal to the square root of 4.5 times 7.5 times 10 to the negative third. And when we calculate x, we get 0.18. And 0.18 is less than 5% of 4.5, so that was a valid assumption. Now, what does that mean? Well, this has two pieces of meaning. One is that the concentration of H plus after this first dissociation is equal to 0.18. It also means that the concentration of H2PO4 1 minus is equal to 0.18. And it means that the concentration of H3PO4 is equal to 4.5 minus 0.18, and that's 4.32. Now let's look at the second dissociation now that we know that stuff. So we begin our second dissociation here with H2PO4 1 minus. And that's going to break down into H pluses and HPO4 2 minus. And Ka for the second step here is 6.2 times 10 to the minus 8th. Initially, well, we know what the H2PO4 concentration was. It's 0.18. We also know that H plus isn't 0 now because we already have some from the first dissociation. In fact, we have 0.18. But we don't have any HPO4 2 minus yet. The change is 1 to 1, so minus x plus x plus x. At equilibrium then, we have 0.18 minus x for the H2PO4. We have 0.18 plus x for the H plus ions, and x for the HPO4 2 minus. So Ka2, which is 6.2 times 10 to the minus 8th, is going to be equal to x times 0.18 plus x divided by 0.18 minus x. Now 10 to the minus 8th is even smaller than 10 to the minus third, so it's probably going to be okay to assume that both in the numerator and the denominator, the x's that are added to 0.18 can be ignored. So we're going to say that this is approximately equal to 0.18x over 0.18, which is, of course, x. So that means x is equal to 6.2 times 10 to the minus 8th. So what's the meaning of that? Well, it means that our concentration of HPO4 2 minus is equal to 6.2 times 10 to the minus 8th after this dissociation. And since our assumption was valid, that 6.2 times 10 to the minus 8th is small compared with 0.18, our concentrations of H2PO4 and H plus are still the same as what they were before, and that is 0.18. So now we'll go to the third dissociation. HPO4 1 minus is dissociating to give H plus and phosphate 3 minus, PO4 3 minus. Ka for this third dissociation is equal to 4.8 times 10 to the negative 13th. So initial concentration of HPO4 1 minus was 6.2 times 10 to the minus 8th. The initial concentration of H plus, well, it's 0.18. The initial concentration of PO4 3 minus, there isn't any yet. The change is 1 to 1 again. At equilibrium then, we have 6.2 times 10 to the minus 8th minus x for HPO4 1 minus, 0.18 plus x for H plus, and x for PO4 3 minus. So 4.8 times 10 to the minus 13th is equal to x times 0.18 plus x divided by 6.2 times 10 to the minus 8th minus x. Now 10 to the minus 13th is very small. So even though 6.2 times 10 to the minus 8th is pretty little itself, I'm going to make the initial assumption that x is ignorable in the denominator here, and it certainly is ignorable in the numerator when compared with the 0.18. So I'm going to say, for now at least, that x times 0.18 is in the numerator, divided by 6.2 times 10 to the minus 8th in the denominator. So I'll multiply both sides by 6.2 times 10 to the minus 8th, and then divide both sides by 0.18, and I will get x. And that works out to 1.7 times 10 to the minus 19th. And 1.7 times 10 to the minus 19th is, in fact, very, very much smaller than 6.2 times 10 to the minus 8th. So our assumption was valid. So here's what this means. This is the concentration of phosphate ion after all this dissociation has taken place. The concentration of HPO4 minus is this at equilibrium. The concentration of H3PO4 is down to 4.32. The concentration of H2PO4 minus is 0.18, and the concentration of H plus after all this is done is still 0.18. So in fact, it is true that the first dissociation gave all of the H pluses that are even worth considering. The next thing we're going to talk about is the potential pH effects of salt solutions. Solutions of salts, of course, have cations and anions, and what we have to do is think about what is the effect of the cation and what is the effect of the anion, and then put them together to determine if there's going to be a pH effect from that individual salt solution. First of all, let's take a look at cations that come from strong bases. Like, for example, think about the base NaOH. This is a base that completely dissociates to give you Na pluses and OH minuses. Now let's think about water. In pure water, HOH, we have this reversible autoionization reaction going on that produces H plus and OH minus. If I introduce some sodium ions into the solution from sodium chloride or some other source of sodium, if it were possible for these sodium ions to react with the OH minus and remove OH minus from solution, producing NaOH, then we would see a decrease in OH minus concentration and an increase in H plus concentration, and then we'd see the pH drop. But of course, NaOH is not going to form from Na and the loose OH minuses that are present from autoionization, because that would mean this irreversible reaction would be running backwards, and that doesn't happen. So for that reason, we know that cations from strong bases are going to give neutral solutions. So this means the group 1s, so Na plus, Li plus, etc., and calcium, strontium, and barium, when those cations are present as part of a salt, the cation has no effect on pH. It will not produce an acid or a base. All other cations, for one reason or another, give acidic solutions. So we may be talking here about something like ammonium, which would give an acidic solution because it will decompose and give you H plus and ammonia. So that's a possibility. Or we could be talking also about something like aluminum, which will make that complex with water and eventually create an acid that way. So for cations, there are only two choices. It's either neutral or it's acidic. Neutral if it came from a strong base, acidic if it's anything else. Now let's look at the anion effect. Let's think about anions that come from strong acids. For example, HCl. HCl ionizes completely to produce H pluses and Cl minuses. This is not a reaction that's going to go backwards. So when you think about water auto-ionizing to give H plus and OH minus, if you introduce chloride ions from some salt like sodium chloride that has chloride in it, if it were possible for the H plus and the Cl minus to get together and make HCl, that would remove H plus from this system and cause it to shift to the right, producing a basic solution. But that reaction is the reverse of this irreversible reaction, and so it's not going to happen. So anions that come from strong acids give neutral solutions. Of course, there are only 6 of these. So if you see the Cl- ion, the Br- ion, the I- ion, nitrate, sulfate, or chlorate ion in solution from any salt, that means it has no effect on pH. Anions that come from the first or second ionization of a polyprotic acid will give acidic solutions. So basically what we're talking about here is any anion that starts with H, like bisulfate here. Bisulfate is going to ionize in water to give you H plus and sulfate, or H2PO4 will ionize to give you H plus and HPO4 2 minus. So in both cases, those anions will produce H pluses and give an acidic solution. All other anions are actually the conjugate bases of weak acids, and so they will have a basic effect on a solution. So let's put these effects together, the cation and the anion effect, and go through all the possibilities that could arise as we examine a particular salt solution. First of all, one possibility with a cation is that it will be a neutral cation. These are cations that come from strong bases, remember, so something like lithium ion or sodium ion. If it's neutral, then we have to ask ourselves, what about the anion? What's the effect that the anion could have? Well, we know that the anion could have 3 possible effects. One of them would be that the anion is an anion from a strong acid, like Cl- or NO3 or something like that. In that case, the anion effect is also neutral. So we have a neutral causing cation with a neutral causing anion, and the end result is you have a neutral solution. But another effect that we have is if we had an anion that comes from the first or second ionization of a polyprotic acid, that anion effect will be to create an acidic solution. So a neutral cation together with an acidic anion is going to result in an acidic solution. The third possibility is that you may have an anion that's a weak base, and this is actually a very common possibility. And so the neutral cation together with the base causing anion will result in a basic solution. What if the cation is acidic? There are no basic cations, so if it's not a neutral causing cation from a strong base, then whatever cation it is, it's acidic. Once we know that the cation is acidic, we have to take a look at the anion and find out what's the effect it would have on the pH of a solution. Well, one possibility is we could have an anion like HSO4 or HCO3 that is an acidic anion. Well, if it's an acidic anion with an acidic cation, the result will be an acidic solution. The other possibility is the anion may be an anion from a strong acid, and those are neutral causing anions. So an acidic cation with a neutral anion will produce also an acidic solution. The third possibility is that we have a basic anion, and this is a common possibility because many anions are weak bases, the conjugate bases of weak acids. So now we have an acidic cation combined with a basic anion. What's the end result? Well, it turns out that we have to ask ourselves an additional question to determine this. We'll have to compare the value of Kb for the base causing anion, with the value of Ka for the acid causing cation, and determine what is the net effect here. Well, we have 3 possibilities, 3 possible outcomes. One is that Kb is bigger than Ka. If Kb is bigger than Ka, then we will end up with a basic solution. Another possibility is that Ka is larger than Kb. In that case, we will end up with an acidic solution, because what it means really is that we have a stronger weak acid than we have a weak base in the solution. The third possibility is that Kb and Ka happen to have the same exact value, and that would result in a neutral solution. So these are all the possibilities that could possibly arise when you throw a salt in water, because it will have a cation and an anion, and the combination of their two effects will be the effect on the overall solution. So let's look at a few examples. Here's the first one, sodium nitrate. The cation is sodium. Sodium will lead to a neutral solution because that's the cation that comes from a strong base. The anion is nitrate, NO3 1-. That will lead to a neutral solution because that's an anion that comes from a strong acid. So the net result is neutral, and neutral means the whole solution is going to be neutral. There will be no effect on pH. Kf. K plus is neutral because it's a group 1. It comes from strong bases. Now let's look at the anion. F minus is the conjugate base of the hydrofluoric acid. So this is going to contribute to a basic solution. Neutral together with base, the only thing that causes any effect is the base, and so this will be a basic solution. Fe3 plus is the cation in FeCl3. This is not from a strong base, so that means it's acidic. Chloride ion, well, this comes from hydrochloric acid, so that means it's going to have a neutral effect on pH because anions that come from strong acids have no effect on pH. So if I look at acid and neutral, the only thing that will cause pH change would be the acidic component, the cation. So this will be an acidic solution. CaSO4, calcium 2 plus, comes from a strong base, neutral. SO4 2 minus comes from a strong acid. It's a conjugate base of sulfuric acid, so that's going to result in a neutral solution. So neutral and neutral, overall result, the solution is neutral. Now here we've got this salt. Ammonium is the cation, NH4 plus. That's an acidic cation. The anion is the acetate ion, C2H3O2 1-, and that's the conjugate base of acetic acid, so it would contribute to a basic solution. What's the end result? Well, we have to compare the Ka from ammonium with the Kb from the acetate ion and find out which one is larger. If I look for the Ka for ammonium, I probably won't be able to find it, but I will be able to find the Kb for its conjugate base, ammonia. Ka for ammonium is going to be Kw divided by the Kb for ammonia. And this ends up being 1 times 10 to the minus 14th, of course, for Ka, divided by 1.8 times 10 to the minus 5th. And if I do the arithmetic here, I get 5.6 times 10 to the minus 10th. So that is the Ka for ammonia. Now let's do the same exercise for acetate. Once again, I'm probably not going to find a Kb for acetate, but I can find the Ka for its conjugate acid. So I can think about it this way. Kb for this base is equal to Kw divided by the Ka for its conjugate, which is acetic acid. And Kw, of course, is 1 times 10 to the minus 14th. And if you look up the Ka for acetic acid, you will find that it is 1.8 times 10 to the minus 5th, which just happens to be the same as the Ka for ammonia as a weak base. And so we'll end up with the same value of Kb that we had for Ka, which is 5.6 times 10 to the minus 10th. So we have one of those fairly rare cases where Ka equals Kb, and that means the end result is the solution will be neutral.